So Max is doing the next presentation, the last of this section, and I guess everybody knows him very well. He's a curator in Burgersoe since 15 years, started in Amsterdam, and will now talk about nitrate and phosphate removal to improve water sustainable practice at Arnhem. Thank you, Max.
Thank you. Well, Marcus told already quite a lot about denitrification, but I think I will cover it very shortly and go to more to the results. But before I start, just a short word about the aquarium. It opened in 2000 and it's far away from natural seawater. It has a total volume of about 8,000 cubic meter, and it has some fish aquaria and some live coral displays. And for us the problem is that, yeah, because you are far away from the sea, you have to reuse the water as maximum as possible. Some of you have seen the aquaria already, so they are not very much packed with fish. Because in comparison to many of your aquaria, it's much lower input of food, but still we have to do some water management. I want to talk about the tunnel display. It's one of the displays where we keep different ray species, different elasmobranchs. Well, in total we have about 550 kilo of body weight in this tank. There is a breeding group of eagle rays in this tank. Different rays, a few sharks, and many teleosts. So what do? We feed, of course. You have to feed the animals, but what do you bring in if you start to feed? I try to create a bit of a budget to know a little bit what is happening in the aquarium, because then you can start to look at possible solutions. So if you feed some food, here we feed about 6 kilo a day, you can calculate it in towards your nitrogen budget and your phosphate budget. So we give about 77 grams of nitrogen per day into the system. The question then is, what happens with that? Of course, you do some water changes, so you lose some of your nutrients. We don't have that much filtration capacity, but most filtration capacity is in the protein skimmers. So for us, most proteins are taken out via the protein skimmers, and that's a good way of getting some of the nutrients out. Of course, you have some increase in biomass. But yeah, most animals are already 10, 15 years old, so they don't grow very much, so I think this will be really, really small. And you can see that there is an increase in dissolved nutrients in the water. And that's exactly where I would like to talk about. So for water changes, we don't do very much. So we do about 77% per year over the last 15 years. You see that the last years we do increase a little bit more, but it's still around 10% per year that we do water changes, which is not so much. So you can only do that when you are removing nutrients from the water. But what nutrients are we looking at? Well, it's the nitrogen and phosphate. That's what I would like to talk about. And yeah, what level should you have? I think this is a table. Yeah, we can talk hours about it, and we also cannot talk hours about it, because I don't know. I don't know what this should be. This is what we use, this is what we have the feeling about. It should be a little bit like this, but I'm sure all of you have other ideas about that. So this could be a real interesting workshop, because it's really important. Where do you want to go to? What is really important for your fish? There is some stuff in literature, and Marcus showed that already, but these are mostly very high levels. Yeah, where should we look at? Well, I want to look now purely at the fish tanks, so not to coral tanks, but to a fish tank, and we try to work towards these levels. Something about the filtration. We have a very simple pre-filtration. Then the water goes through protein skimmers and through a trickling tower. That's the simple system we have. The trickling tower is a big PVC pipe, as you can see here, about 3-4 meters high, filled with these plastic rings, and they are good for the nitrification. In total, it's a flow of about 140 cubic meter per hour. So every 11 hours, 12 hours, the whole volume goes through the filter, which is not so much. You see it also in the water quality because it's not clear. It's not a crystal clear tank, but we don't mind. We don't mind that it's not always crystal clear, that you don't see exactly what time it is in the back of this room. So here we try to work with, and for a couple of years it went quite well, but then you see the nitrates going up, of course. And how far does it go? Where is your set point? These are questions you have to look at, and you have to do something. So at 4 or 5 years running the tank, we decided to start to introduce a denitrification system. Also, when you look at the input, this is purely the input we bring into the system purely on food. So this time I say all the food we bring into the system will come as nitrogen, nitrate nitrogen into the water. This is of course not right, but I make the mistake over the whole series of time. So that means that in the beginning we only had a few fish or small fish in the tank, and yeah, the fish are growing and more fish are introduced, so you have to feed more. Yeah, and this will only make the graph more exponential in the future. So you have to do something, or you have to start doing big water changes, or you have to start to do denitrification. Well, we were starting with a denitrification system. This is a methanol system. It's a very simple tank. It's an upflow tank. It's just a PVC tank, about 800 liter in size for this tunnel display. We can adjust the flow, the amount of flow that goes through. This one runs at around 100 liter per hour. And I didn't know how big it should have been. I really didn't know what should we expect of such a filter. So for us it was also a bit of an experiment to see, does this work or does this not work? And well, you will see if it works for us or not. It's filled with these plastic rings. And it's a very open system. We first wanted to have more smaller rings, so it's more closed system, but yeah, especially with methanol, it's a heterotrophic bacteria growth, and it's an enormous amount of biomass that is produced within that filter. So nearly every day we have to skim the surface of this filter, which is just open for the air. So this is where it overflows. And there's a lot of biomass growing there, just coming from the rings, and it's floating on the surface. So we have to remove that from the aquarium. If we just look in schematic to the aquarium, or to the filter, it's an upflow system, and there are different things happening. If you start to introduce methanol or ethanol, it will first react chemically with oxygen. So, of course, part of your oxygen will be used by bacteria which are growing underneath in the deepest layer of the filter bed, but you also have this chemical activity. So you do lose some of your methanol that you are introducing into the filter already purely because of your oxygen. A next step, and that's the step what you really want to have, is that the methanol will be consumed by the bacteria and that they will produce nitrogen gas. The good thing for me, an extra thing for this methanol filter is also that they produce hydroxides. So you will see an increase in pH, which is really good because always when you have fish in a tank, your pH will start to drop because of nitrification, because of CO2 production. And especially when you have a filter like this in your system, you don't have much pH problems anymore. So if we start to calculate a little bit on this, then you have an oxygen depletion, which you lose some of your methanol, which you add to the system. Again, you have a nitrate depletion. That's the idea of the whole denitrification filter. So in this example, we go from 40 milligrams nitrogen to around 15 milligrams, and that consumes about 150 millimoles per hour. So in total, if you bring in about a liter of 15% methanol a day into such a system, you will remove about 50 grams of nitrogen per day. And that's mostly enough for us. In any case, for the application in the aquarium for us. You can see it in the results that the nitrate level, since we are using, at this point here, we have been introducing the denitrification system, and the nitrate level is is not increasing anymore. You do see some dips and steps, and sometimes something goes wrong. Management problems, technical failures, okay, always helps to have some movement in your figures, but most of the time you can conclude that it's a stable level. Only in the end here, we were playing with the amount of methanol, so we started to introduce a little bit more methanol because it was really increasing too much. So we're starting to introduce more methanol into the filter, and it's dropping again. It's a very, very slow system. I mean, this is a 15-year period, and it does not change your nitrate level just like that. It takes half a year or even that to stabilize it, to get it properly running. But that's because it's a very small system. We don't need a huge system when you have not so much animals in the tank. I was really happy doing this, and I was really happy to see that the nitrate level was stable. But then you come to the next step, because you're still not doing much water changes. There are other things that are happening in your water. Well, one of the other things is the phosphate. It takes a few years longer, but then also the phosphate is going up very heavily. We just had a discussion what happens with your phosphate when you have a denitrification system. Well, there is still some removal of phosphate inside a denitrification filter, in any case in this denitrification filter, because there is a lot of biomass built up. So in this heterotrophic filter, there's a lot of biomass built up, and phosphates are included within that biomass. And as long as you remove this biomass, or just manually, or via the protein skimmer, which is in the next step after the denitrification, it's a very good way of getting rid of some of your phosphates. But still, it started to rise. And I have no idea what it should be. So I just say, okay, it should be 4. But we can also do 6 or 7 or 2, or I don't know. I really don't know. But I had a feeling, if I wait, it will become a problem, maybe. And if it's a problem, then we have a problem. Then we cannot solve it just like that. We cannot do 100% water change in one day. It takes a long, long time to get rid of that problem. So before it becomes a problem, it's better to start to look at alternatives for phosphate removal. Well, there are different techniques for phosphate removal, but for such a big tank as this, resins, phosphate removal resins, are very, very expensive. So we decided to have another system. We do it with iron chloride. It's an iron chloride system. So we add here with a dosing pump iron chloride to a mixing container, and from there the water, the seawater, and the iron chloride will go through this old shark transport tank, which is rebuilt into a phosphate filter. It's a very slow system. We have different materials. We started with this as being the material, the media, where the stuff precipitates on. But the team was thinking about could we not do that easier? So they rebuilt a system, and now we are using these very small, tiny rings, which you also can see, I think, in bead filters. And it's a tub filled with these rings, and in these rings the stuff will precipitate, and when you put some air underneath, you wash it very easily and you can drain it to sewage. So it's a very easy technique to get rid of your dirt. So what happens in such a filter chemically? It's not a biological filter, it's purely a chemical filter. So if you add some iron chloride to your water, the iron will react with phosphate. Great, that's what you want. The iron phosphate will not be the only one that is produced, because you also have iron hydroxide production. And that's a pity, because you lose hydroxides. And this ratio is about 1 to 1. So for every molecule of phosphate you want to take out, you also take out hydroxides. So you have to add extra hydroxides after this filter to the system, because else you will have pH problems. These two are combining into a complex, and also organics will fix on this complex. And that's very good. Some people use this also on their sand filter, just in front of their sand filter. Just add iron chloride, and you'll have much more coagulation and much more easy getting rid of organics from your water and will stay into your sand filter. We do it in this way. We add about 200 milliliter of iron chloride per day, and we remove about 7 grams of phosphate per day. But the disadvantage, the really big disadvantage is that you lose a lot of hydroxide. So you do have to add extra hydroxide. Again, a chemical extra. And all these chemicals, you were just saying something about ozone safety. That's of course with these guys also, you really have to be careful when managing all these different chemicals. Both iron chloride and sodium hydroxide are not so friendly chemicals, so you have to be careful with that. So what's the result? The result was that the phosphate level, the blue dots, increased in the first 8-9 years, and then we introduced the phosphate filter, and it dropped to a certain level, and there it's about that level. And I'm playing with that filter to keep it on that level. We can go deeper if we really want to, but why should we? We say the set point is at the moment 4 milligrams of P per liter, so why do you want to go deeper? As a conclusion, you can do very little filtration on a system like what we have. And every aquarium has, of course, their own system and their own choices, their own values, how good should the water quality be. But with the system we have and with the water quality we want to have, 11.5 hours per is enough for filtration once every 11.5 hours. And even when you have only water change, an average of about 8% per year, it's possible to maintain. But you do need to have denitrification and phosphate removal, and then it's possible to do these small water changes. I think it's a very handy tools to work with. It's not always easy, especially not understanding what is happening, because the better you can understand how such a system works, the easier it is to adjust things. And there are still some black boxes in the filters for us, but I think it helps us in any case a lot. But the final thing is, how long can we keep on doing this? How long can you proceed in closing the loop, doing very little water changes? I don't know. This is an open question, but I don't know. If I look at the nitrates and I look at the phosphates and think, okay, that's at the moment under control, but what are all these other things happening in the water? There are more chemicals within the water that may build up and become a problem for the fish. So maybe you guys have an idea how far we can go on. Thank you for your attention.
Thank you very much, Max, for this very nice, interesting presentation. We are perfectly back in time, so if you have any questions now, Pete?
Hi Max, did you look after the minor elements, for instance? Because you mentioned, okay, we don't know what really happens, but did you some measurements about minor elements after the phosphate and nitrate identification?
Which minor elements do you mean?
It doesn't matter, selenium or iodine or that kind of
well, we do measure now and then the trace elements and the macro elements in the system. And it is a bit lower than what we have, for example, in our coral system. Yeah, and is it too low or not too low? It's still within 75–80% of what you normally would find in natural water.
But it's not in the range that you said, okay, I have to put more from those minor elements in it?
Not for fish system, we don't do that now. But maybe for coral system we do that a lot, but not for a fish system.
Okay,
no.
Thank you.
Okay, more? Yep, over there.
I'm not quite sure. I remember that you had a nitrate value of about 20 milligrams per liter. And I think Mr. Denyatin also reported about 20 milligrams per liter. Is that right?
Well, yes, that's right, but it's also not right, because Marcus was saying 20 milligram nitrate per liter, and I'm saying 20 milligram nitrate.
This was the question, yes,
Yeah,
exactly.
so that's the difference.
Yeah, the factor between that is about 4. So you are reporting about 80 milligram nitrate, and Mr. Danyati is about 20. So
Yes.
just to this is the right understanding of this
Yeah,
number.
but there is a difference in what you have on collection in your aquarium. So this was purely a fish tank.
Okay.
And for Marcus, there was also corals in there,
Of
so
course.
that's a different approach.
Just understanding to compare the two reports.
Okay, so I think we're going to close this session, and I would like to thank all the speakers for the nice talks and for keeping in time.